Okay, in this video we'll determine the coordinates of every turning point and inflection point for this function f of x, and that is 6 times the cube root of x minus 2x. And once we piece that information together, we might even try sketching the function before, of course, we have maybe a look at Desmos towards the end of the video. So let's get ready for our first derivative and start determining intervals of increase or decrease, and then, of course, see if we have any turning points. But before we do that, we better get rid of our radical. Not get rid of it, but rewrite it. So this is going to be 6 times x to the power of 1/3. And then subtract 2x, and now our first derivative isn't much of a problem. It'll be 6 times the power of 1/3 that comes down, then x, and the power will be 1/3 minus 1, which is going to be negative 2/3. Of course, we can clean that coefficient up and then differentiate minus 2x to get minus 2. So our derivative, or our first derivative, is going to be 6 over 3, which of course is 2. And maybe we'll write a negative power one more time. So it's going to be negative 2/3 subtract 2. So we need to figure out what makes our first derivative undefined or equal to 0. So it's probably a good idea to get rid of the negative power and rewrite this as a radical again. So this is 2 divided by the cube root of x squared. And then we have a subtract 2. So we can see one definite critical value is going to be x equals 0, because that makes our first derivative undefined. Let's see if we can make this first derivative 0, though, to see if there are any other turning points. So this will be a little bit more demanding algebraically. So let's set our derivative equal to 0. And maybe instead of rewriting this whole expression again, you can visualize that and think I'm probably going to add 2 to both sides. So let's at least maybe do that in one step. So I've set my derivative equal to 0, and I'll add 2 to both sides. So I'll get 2 on one side, and that has to be equal to 2 over the cube root of x squared. Or realizing this term, 2 over x cube root of x squared has to be 2, so 2 minus 2 will be 0. We could do reciprocals there, or just multiply both sides of that derivative by that cube root of x squared, of course, and that will give me 2 by the cube root, multiplied by the cube root of x squared, equaling 2. And of course we can divide the 2's, and that's gone. Well, not completely gone, we'll have 1's as a coefficient, and as a constant on the right hand side. So I just divided our equation by 2, and that radical is a bit nasty to deal with, so I guess we could cube both sides, which is actually probably a good idea. I find if you go to fractional or rational exponents, sometimes you might lose track of one answer here, because note the x squared, and if I switch that to x to the power of 2/3 again, I honestly might forget that I need a plus or a minus in there, and you might actually be in the same situation. So let's cube both sides, and we'll get the familiar x squared equals something. So I think our brains should probably tell us we need a plus or minus. Then when we cube the number 1, well, that stays 1, which is kind of convenient. And now make sure that we pick up another pair of critical values with the square root principle here. So x is going to be plus or minus root 1, which I think we can safely write as 1 now. So we have 3 critical values. Seems like an excess of critical values, but we have 0, and we'll have plus or minus 1. So we're going to have a little bit of work to do in our sign diagram. And that being said, I probably should go back up until I can see our derivative before we do our sign diagram. And if I stay there, we can see the critical values and our derivative. So sign diagram right here. And we need plus or minus 1 and 0. And probably should label that as our first derivative, because we still have some second derivative work to do as well. Okay, so we have our work cut out for us here with 4 different regions, but most importantly, that's a bit of a nasty derivative to evaluate without a calculator. So feel free to just use some numbers in those 4 different regions and use your calc, but I'll be brave and foolish and try to do it without a calculator. So I'll start with a number to the right of 1, and I'm going to pick square root of 8. And at first that might seem like a strange idea, but if I put the square root of 8 into this function, and keep in mind that is to the right of 1, the reason I'm using root 8 because we have to square that in the denominator before we'd have to take the cube root. So if you're a bit creative, and I think you can use your imagination with me here, square root 8, you get 8. So if you use your imagination, you can actually avoid a calculator. Not that I think you need to, but just see if we can as a challenge at least. So that's going to be 2 over 2, so that's going to be 1 minus 2. So we have our first region. We know our function is coming down, it's decreasing here. So 1 down. So let's stick with the root 8 theme, and we'll go to the negative root 8, and I guess the very leftmost region. And if I put a negative root 8 into my derivative, I'm going to square that again, so that's going to be positive. So it's going to be the same thing. This is going to give me exactly the same number. So it's going to give me the cube root of negative root 8 squared, which is positive 8. And once again, we're going to get 1 minus 2. So our function is decreasing to the left of negative 1. I guess I should put some negatives there as well. Okay, so 2 down, 2 more to go, and we can rely on the symmetry here on either side of 0, and probably only really have to do 1 more, again, if we're creative. So if I can get the cube root of some kind of an 8, well, why don't we just put 1 over the square root of 8? We know that's going to be somewhere between 0 and 1. So check this out. If we go f prime of 1 over the square root of 8, which might seem strange again until we see what happens. This is going to be 2 divided by the cube root of 1 over root 8 squared, which is 1 squared over root 8 squared. So that's going to be 1/8 minus 2. So maybe we should do one extra step. So the cube root of 8 is going to be 1/2. So I have 2 on the top, and now I'm dividing by 1/2. And that's going to turn into a 4 minus 2, and I just confirm that to the right of 0, our function is increasing. So let's go with one more. If we put a negative root 8 in there, let's just think about it here without rewriting it all. That's not going to change anything because, of course, when we square that negative 1 over the square root of 8, it's going to turn into an 8th again. So we're going to exactly the same number output, and most importantly, it's positive. So we got some interesting behavior happening on either side of 0. Our function is increasing on either side. But we see, so there's no turning point there, but we see a definite sign change on either side of those other 2 critical values. So right now we know we have some turning points. We only have 2 turning points, so I'll just say turning points. Why don't we just say TPs? We got enough work to do. So TPs, and that's going to happen at -1 and whatever that function value is. We evaluate it at -1, and the same thing with +1. Because keep in mind our imaginary tangent lines here. Remember, -1 and +1 made our derivative 0, so I know there's a horizontal tangent right at x equals ±1, and our function comes down, function comes up. There's some weirdness going on at 0. But we'll deal with that in a few more seconds, and keep in mind our function increases here, so maybe I should move that a little bit. Get the same color back. And maybe a pen too. So there's a horizontal tangent at x equals 1 as well, and our function goes up to the left and comes down. So those are our turning points, and maybe we should label them as well. So this at -1, that's a local min. And of course, the other one's a local max due to the contour from the tangent. So I guess you can memorize it, but I just like to sketch some pretend tangent slopes, and I think it's pretty obvious what kind of what kind of a turning point you have. You can classify it as a min or a max. So let's evaluate our function now. So we've got lots of busy work to do in addition, of course, to the calculus. So what happens when we put in x equals ±1 into this function? So we will get, just up here is scrap work, f of 1, start with the +1. The cube root of 1 is just going to be 1, so that works out nicely. So it's going to be 6 times 1 minus 2 times 1. That looks like it's going to be 4. And I would expect negative 1 to behave very similar to that. It's going to be 6 times the cube root of negative 1, which is negative 1. And then we better watch our sign change here, or at least I better watch it. Looks like we're going to get negative 6 plus 2. So negative 4. So at negative 1, the y value is negative 4. And at positive 1, the y value is 4. I'll just put those in as yellow. So maybe before we go to our second derivative, let's maybe think about what's happening at x equals 0, and the second derivative might uncover something else for us. But that critical value came from our first derivative being undefined. So remember, you have an undefined first derivative. If your slope is a tangent slope is a vertical, has a vertical slope, or you could just say a vertical tangent. It's possible we would have some kind of a sharp point or a cusp, but again, with no difference, with the function increasing on either side of 0, to me that rules out a sharp point or a cusp. I guess we should make sure our function actually exists at x equals 0, and it's in the domain of the function, and of course it's just a cube root. So if I put 0 into that function, I get 0 back again, so I don't have to worry about any kind of discontinuity or asymptote. So it has to be a vertical tangent because it's a number that made our first derivative undefined, and because our function didn't, it's not a turning point at x equals 0, it rules out the notion of a sharp point or cusp. So let's go with a vertical tangent there at x equals 0. We'll just say vertical tangent. That's the only option that it can be, but please keep in mind I did evaluate my function and I figured out that it actually output something. So there's a vertical tangent. Why don't we just put the ordered pair here at the origin? So make sure your function's defined, otherwise you can't just say it's a vertical tangent. It very well could be a vertical asymptote or some kind of a discontinuity. Okay, so I think we've eked as much details as we can out of that first derivative. Let's find our first derivative again and keep the ball, I guess, rolling here towards the second derivative, and we'll start looking at concavity. So let's maybe copy this and get some space all the way down to here. There's our first derivative, and we, of course, I grabbed the one with the rational exponent, so now we can just go proceed to our second derivative in a different color here. So f double prime of x is sidestep the 2, and then the negative 2/3 comes down. Subtract 1 from that, so this is going to give me negative 5/3 as a power on that x, and then when we differentiate the constant, goodbye, it's gone. And let's write that as a radical again to recognize our only possible inflection point. So what do we have as a coefficient? We got negative 4/3. I guess I forgot I'm supposed to be writing that as a radical again. So we got a negative 4/3 coefficient. So let's just say minus. We'll put the 4 on the top. We'll put the 3 on the bottom. And we'll switch this negative 5/3, I guess, first to x to the power of 5/3 in the denominator. And then, of course, the 3 is your index. So this is a cube root of x to the power of 5. Once that comes down to the denominator. And that's just to make it painfully obvious that our possible inflection point, we can't make this expression equal to 0 because we have no x's in the numerator. So the only possible inflection point we have, possible IP, is going to happen at x equals 0, that origin again, where I strongly suspect, actually I'm 100% confident and convinced that it's a vertical tangent, so that it's possible that we have a, I guess, a change in our concavity there as well, but of course we have to confirm that with a sign diagram, because a lot of vertical tangents actually change concavity. I hate to say always, but I would say most of the time for sure. So our only possible inflection point is 0. So let's pick something to the left of 0. Negative 1's as good as any, and then I'm going to get the cube root of negative 1, so I'm going to get minus 4 all over a negative 3. Once I figure it's going to be 3 times that negative 1. So this is going to be positive to the left of 0. So right now that means my function is concave up. And then let's test one other one. Of course, we'll take plus 1, the right-hand side of 0. And when I put that into our second derivative, we're going to get 3 times 1, not 3 times negative 1 like we did on the left-hand side there. So now we get a negative value in our second derivative. So our function is concave down. It switches concavity. So we just confirmed that at that vertical tangent, we also have an inflection point. Okay, so our inflection point is at x equals 0, and we already know that ordered pair, so we can finally start, I guess, to piece some of this stuff together. So keep in mind our IP, where will I write it? How about right underneath here, our inflection point, it's going to happen at 0 and 0. It's also the location of our vertical tangent. So lots of interesting business going on there at that origin. So let's see. Of course, our question really was just, find your coordinates of your inflection point. And I guess I can therefore that, or box it at least. We did that. Get the coordinates of your turning points. And it didn't ask us to classify them, but it did that as well, because you probably should always classify your turning points. So we answered the question, but of course, this whole topic should culminate in you using all this stuff to sketch curves. So as we wrap up this chapter finally here, in the next maybe 1 or 2 more videos, we'll focus on just doing all this for the purpose of sketching the curve. So let's see if we can sketch this curve, at least something. And then ask ourselves, I guess, what we have here right now. Well, I got a point at the origin where there's lots of funny business happening. I had some turning points, so let's go back up and remind ourselves. Those turning points, we're at -1 and -4 and 1 and 4. So of course my diagram's not going to be to scale there, but let's just try to stay somewhat consistent with tick marks. That'll be -1, that'll be +1, and then I'll just say that's 4, and that's -4. I'll label that in a second. So yeah, the negative x got the negative y, and the positive x got the positive y. So I better stick a 4 there and a -4 there. Okay, so that's not a lot to go on. That could be a straight line, be a cubic polynomial, but remember it is a cube root function that we're dealing with here. So let's keep putting some other details in here. So we got a min at the negative ordered pair and a max at the other one. So let's scribble that underneath. We'll just say this is a local min. You don't have to copy it down, of course, but just at least think it. And this is a local max. So of course, if this is a minimum value, of course, it's going to turn around here. And this is a maximum value. It's going to turn around here. I also better start to think about that vertical tangent. So let's maybe connect this part. This would make sense. Let's come in here, snug up to that y-axis, and try to make this function as vertical as I can on this tablet. I think the trick is to go fast. There we go. That's not bad. So right now, that's what it's doing. Now, of course, the tangent slope is supposed to be completely vertical at the origin there, but we'll rely on Desmos for that. Now, does that jive with our concavity? What was our concavity to the left? It was concave up. Okay, so that's making sense as well. We definitely have a concave up section of our function here, and I guess I don't need to label it, but I'll stick it here. And this is concave down, and these labels, of course, you don't have to put them on, but since I can't see everything on the screen at one time, it's a good idea. So we can just extend that curve and probably be done with it, I think, at this point. But of course, if you want to get your possible X-intercepts, you could. And who could pass up such a good time? So let's go have a quick look at the X-intercepts up here. So we need to figure out what makes our function or our y equal to 0. So it would have to be, well, let's write this as a rational exponent, so a power of a third, and then minus 2x. So how do we make this equal to 0? Well, maybe with great difficulty, unless you just pull out the common factor. Now we can also take a 2, but the one that matters the most is doing the common factor of x to the smallest power, which of course is x to the power of a third versus power of 1. And then this is going to be 3 minus x to some power that I have to add to this other power once we multiply, right, to get 1. So that's going to be 2/3 where I have my question mark. And I accidentally got rid of my bracket too, but we can fix that. Okay, so let's double check with our expanding this out before we go ahead and confirm at least our exact X-intercepts. But I guess if you have a calculator handy, they would be useful to have on your graph. Give you, I guess, more confidence and everything, all the pieces are fitting together. So multiply this out, we get 6 to the times x to the 3rd, which is correct. And then over here I get 2, and the x times that x, we add those exponents, we get 1, so we're good. So this first factor, our common factor, can definitely be 0 if x is 0, and we know that already a couple of times over at this point. So this is the new one. Of course, those fractional or rational exponents are fun. So we'll set that equal to 0. So I'm just going to add that to both sides since I'm pretty limited in space here. So 3 has to be the same as x to the 2/3 in order to get a 0 out of that second factor. And watch that numerator. Anytime there's an even power and a fractional exponent, that means you are taking an even root. So it's probably best to do it in 2 steps. Let's cube both sides. And that's going to get rid of the 3 on the bottom. Getting rid of a cube root. You don't have to worry about plus or minuses is essentially what I'm doing there. So it's going to be 27 equals x squared. And now I think if you see it that way, at least I know if I do, I'm not going to screw up and forget my plus or minus. So it's going to be plus or minus the square root of 27. Okay, so I just took a few moments there and wrestled with the tablet, but I think I eventually got something that resembles the function. And since we took a few minutes, just make sure we know what those x-intercepts are. Again, they're supposed to be roughly 5, which they don't look like they're 5, which is why I will label them as roughly 5 and 0, and negative roughly 5, and not 25, roughly 5 and 0 as well. So the x-intercept work was, I guess, bonus fun thrown in here, and it didn't really help me with the sketch because the concavity and the vertical tangent and the turning points already looked after that as well. So let's okay, so here we are in Desmos, and I guess first things first, root 27. You can see it's 5.20 or 5.196 negative and positive. So we definitely got that correct. We have an x-intercept at the origin, but I think most importantly it is a vertical tangent as well. So let's see if we can get that to stick at 0. It's a little jumpy around there as always with a vertical tangent. So there it is, vertical tangent. The function is not differentiable there because the tangent slope does not exist. It's a vertical tangent line. So that's why the tangent line disappeared and the slope of the curve is straight up and down right at that point of tangency. Maybe we'll deal with decreasing or increasing intervals. We can see negative tangent slopes, so our function values are going down until they hit -1, and then the function has a horizontal tangent there. And since it now starts to go up with positive tangent slopes, of course that made that a turning point at -1 and -4. And then our function keeps increasing even through the weird vertical tangent point of tangency there at x equals 0. It's really jumpy. There we go. But it still increases after that. If I can get that to slightly go by, which I did, you can still see positive tangent slopes till it hits 1, and then it peters out with another horizontal tangent, which is a stationary point, but better than that, it's a turning point because our function turns around with negative tangent slopes now and decreases. So since we're over to the right, let's take a look. All our tangent tangent lines are on top of the curve, so that's concave down, and then once it gets to the left of the origin, right about there, we can see it's now under, all the tangent lines are underneath the curve, so it's concave up. So of course we have that feature. We already predetermined that with our second derivative work. Okay, so there we have it. That was a more challenging function to sketch, but once again, I think 2 videos in a row now, I've demonstrated that whatever information you can glean from your first 2 derivatives is usually sufficient to get a pretty good idea of what your function looks like and understand the behavior of your function before, of course, you rely on graphing technology. So we've officially entered the realm of curve sketching, where we put all our first and second derivative information to work with the purpose of sketching a curve. We'll look at one or two more examples as we wrap up this topic before we get into applications of the derivative and possibly more interesting applications of the derivative.